Welcome everyone to the Hierarchical Time Series and Machine Learning session. Today we have two presentations. Both are from students, so please remember to give your feedback at the end of the session. And in the interest of time, Amud, please go ahead.
All right, thank you. Welcome everyone. My name is Arnoud Wellens. I'm a second-year PhD student at the KU Leuven, and it's a real honor that I may present you this work that I worked on together with Maxi Udenio and Robert Boete. And this presentation will be all about how to use transfer learning to reduce the computational efforts of the M5 winning methods. So in today's presentation, we will focus on the winning methods of the M5 accuracy competition. As you probably all have heard of this already, but I will quickly go over it again for those who haven't heard about it. It's a large-scale forecasting competition on the hierarchical data set of Walmart. And what else was very interesting is that the top 5 methods substantially outperformed the benchmarks with roughly 20%. And in addition to that, most of the top 50 top performing methods, they almost all use a similar strategy. Most of them use the global bottom-up LightGBM methods. So to briefly explain you these methods, here you can see the hierarchical structure of the data set of Walmart. Well, those methods, they started from the bottom up. So they focused on the time series at the product store level. They grouped these together. They pulled this together, for example, per store, but also per category, per department. And then they trained one global LightGBM model per group of time series. And the advantages of this were, well, apparently it was very accurate, as most of the top 50 performing methods use this, but it's also relatively easy to implement in practice regarding modeling these models, as they typically require less hyperparameters than other sophisticated machine learning methods, but they also do not require an extensive pre-processing of the data set. However, implementing these methods can actually be hard to train in terms of computational requirements. So why is this? Well, complexity comes with a computational cost, as you could also see in the last M forecasting competition. The top 3 methods there, they actually require 35 times more computation time than another famous benchmark, ETS. If we look at the winning method of the M5, well, they trained 220 global LightGBM models for a limited 10-store data set. Well, we also trained these on our relatively expensive server, and that took like around 10 to 20 minutes to train each. So while 20 minutes is not a lot, it can actually add up rather quickly in large-scale settings. So take a retailer, for example. Walmart can have over 200,000 products in one store, and they are currently operating over 10,500 stores. If they want to make one forecast a day for every product in every store, they need to forecast more than 2,000 million forecasts. If you want to do this with the M5 winning method, you need to train more than 15 million models. And this is even worse for like the online marketplace of Walmart. Let's say you want to forecast per product in every region, and a region can be defined as every region with another zip code. Well, if you then want to use the M5 winning method, you actually need almost to model 15 billion models. And the problem here is it's also not a one-time investment training all these models. You typically want to retrain these models periodically when new data comes available or when new products are launched or even new stores. Next to that, it's also not a problem only in retail. There are also other large-scale settings such as Google Ads, search, YouTube, etc. So we actually want to tackle this problem. We were interested in how can we reduce the computational cost of these top performing methods of the M5 accuracy competition to facilitate the practical application. And then we came up with the idea of transfer learning. And transfer learning, let me briefly explain this concept. It's not too hard to understand. It's basically you want to utilize the knowledge from other tasks that you learned before, which you can call the source tasks, to facilitate learning of a new task, which is then called the target task. And this is something very natural that we human beings do. And let's say you learned how to play tennis when you were younger. Yeah, you will then reuse that knowledge, reuse that experience to learn later another skill, such as playing ping pong. However, with machine learning models, it does not come naturally. Typically, if you have different tasks, you learn different methods on separate data sets. Everything is separate. So you really need to model this explicitly. And you need a way to define what are the source tasks, what is the knowledge, how do we transfer this. And transfer learning is nothing new in forecasting. You have a couple of papers using this, mainly for when the target task has too little training data to fully train a model on. So let's say you're a retailer and you want to forecast the sales of a newly launched product. Well, you typically don't have enough training data to completely model that forecasting model. So in that sense, you want to reuse knowledge. However, in our case, well, we assume that we have enough data. We simply do not want to use all the data to speed up training. So then we came up with the following question. Like, if those top performing methods of the M5 all build separate models for each store, but also for each category, each department from scratch, can't we like reuse the knowledge, as we believe that those models are somehow related? And why do we believe this? Well, these stores, they sell similar products, they can have similar levels of seasonality, similar interactions, etc. And to prove that this idea is not too weird, there are actually papers already using a similar idea. One of them implemented this using neural networks on Flipkart, one of India's largest e-retailers. However, they do not analyze the reduction in computation time, or they do not analyze the effects on the accuracy as well. Another reason is that the suboptimal selection of hyperparameters and forecasting models may have a neglectable small effect on the forecast accuracy. So we believe that this maybe suboptimal strategy of using transfer learning may not be too negative in terms of the forecast accuracy. Why is this the case? Well, because your out-of-sample test set is never exactly the same as your training data. So to give you a quick overview of our transfer learning framework, the first step here is to train general models. So how does this work? Well, given a set of global models at grouping level G, so these can be the top performing methods at the store level, well, we will train these models exactly the same, but at a higher aggregation level. So at level G prime, which we call a source model. So then in the end, you will have similar models that you will learn from scratch, but as they are similar sized, you will need less training time. And then secondly, we will improve the forecast accuracy of these models by firstly transferring these models back to the lower level, and then fine-tuning these target models with data specifically from level G. And in that way, we want to replicate the global models at grouping level G, but with lower computational requirements. So to better explain this idea, let me go to the following slides. So we want to replicate the recursive store level LightGBM models. So these were the models that also the top performing method of the M5 used, but also many other participants. And as explained before, these models pool the data from the lowest level together per store, and then they train one LightGBM model per store from scratch. We are going to train, well, we trained the exact same models, but at a higher aggregation level. So in this case, at the state level. So now we are not training 10 models, but 3 models instead. And they are similarly sized. So what do I mean with that is we use exactly the same features and exactly the same hyperparameters. Maybe one small note on this, because the hyperparameters are optimally determined for the store level, given a certain amount of training data, we also need to use the same amount of training data or some hyperparameters that imply the regularization, for example, would not make any sense. So we also need to reduce the training data for these state models. Why do we need to reduce it? Well, because the state incorporates 3 to 4 stores, it also has 3 to 4 more training data available to it. So if these 3 models are trained, then we will transfer this back to the lower level G, to the store level, and then we can actually make predictions. However, even though we have a reduction in the training time of 70%, as we only train 3 models instead of 10, those source models are less accurate because, well, we're not using all the available training data and we're using suboptimal features and hyperparameters. And because we're using the features that were determined for level G and not necessarily for G prime, so for the state level. So we need a second step here. We need to fine tune these target models. And by doing so, we really want to focus on the store specific patterns by only using training data of the target store. How can we fine-tune decision trees or these LightGBM methods? Well, there have been different fine-tuning strategies being proposed. We are using the pre-built LightGBM function, the refit function. So what does this refit function do? It actually fixes many model parameters once you transfer it, and it only recomputes a small set of the parameters. Only the prediction values of the leaves will be recomputed using the new training data. Instead of using all the available training data, as the top performing method did, we will only use 1 year of training data. Why can we use less? Well, because we're fixing so many model parameters from the source models, there is a low risk of overfitting, as we believe. And as we do not recompute all the available parameters using the refit function, and because we use less training data, the computational requirements of this step are also much lower than training the models from scratch. So if we put all of this together, we get the following results on the test set of the M5 competition. So on the vertical axis, you see the WRMSSE, and that's the official M5 metric. And on the horizontal axis, you will see the 3 different models. So on the left-hand side, you see the recursive store level LightGBM models. So those are the models that we want to replicate. We use the exact same parameters as the top performing method there. Then we have our transfer learning framework that I just explained. And then on the right-hand side, you have the source models. And the source models are exactly the same as the transfer learning framework, but without the fine-tuning. And what you can see here is that on the test set, our transfer learning framework can achieve similar levels of forecast accuracy as the models we want to replicate. And our source models, they perform slightly worse, at 4 to 5% less accurate. So let us go to the next figure. Here I show a similar picture, but now on the horizontal axis, you have the training time in minutes. So here you can see the difference in the total computational requirements to train these 3 different types of models. And on the right-hand side, you see the recursive store level LightGBM models. They needed in total 200 minutes to train, while our transfer learning framework needs 25% less. And as you can see, the source models, they need even less, only 70%, as I mentioned before. These were all aggregates, right? So let us also look for a moment at the 12 different hierarchical levels of the M5 competition. If we do that, we see that the transfer learning framework outperforms the recursive store level LightGBM models at the more aggregated levels, up to 5%, while it slightly underperforms at the more disaggregated levels, up to -1%. The source models, however, they consistently underperform up to -10%. So then we will go to my conclusion slide. So we propose an easy-to-use transfer learning framework. Why is this easy to use? Well, we simply use the hierarchy of the time series to cluster them. To reduce the amount of training time, we simply randomly select the data points, and we also use the pre-built refit function. So that means that with very little coding, we could actually achieve this from the top performing methods. By doing so, we could reduce the training times by 25% while achieving similar levels of forecast accuracy on the test set for the recursive store level LightGBM models. Then without the fine tuning, we can actually decrease the training time even further with a limited reduction in the forecast accuracy. There are also some limitations to the research. First of all, this very simple implementation has no guarantee of success. I mean, there is no guarantee that we will achieve similar levels of forecast accuracy. I think for that, we will need more advanced fine-tuning strategies that can revise more model parameters or use a more advanced cluster algorithms. And then secondly, the refit function that we use is also poorly optimized in the sense that it needs much more RAM memory than when you learn from scratch using a similar amount of parameters and a similar amount of training data. And it also needs much more training time per parameter. So we believe that it's less optimized than the main function, the main train function of LightGBM. So further improvements are definitely possible. So this was my presentation in a nutshell. I hope you all learned something. If there are any questions, feel free to ask. I would be very glad to answer them. Thank you.
Thank you, Arnoud. We have quite a few minutes for questions, so please either use your chat or just unmute yourselves and ask.
So I can start, I can ask a question. Could this approach be generalized to other models, or it's solely on LightGBM because you use the refit function? So if you can use that on more complex models which do not require like 11 minutes of training time, that require like 3 hours of training time or 5 hours and so on, this could be very helpful. But I mean, okay, 11 minutes are 11 minutes, and if you have thousands of models, it's helpful. It would be much more helpful if it is on much more complex models. Could that be generalized? What do you think?
I think in the case of neural networks, definitely, as one of the references I showed, they actually implemented on neural networks. So what they did there was, firstly, they built I think it was a recurrent neural network on all the time series, so on all the sales data of one e-retailer. And then in a second phase, they used transfer learning and only used the time series from each product category to further fine-tune that. So that's actually a very similar approach as we did, but then they applied it on neural networks. So I think you can definitely apply it there. For other methods, I'm not that sure. I think I do not know enough about many other statistical and machine learning methods to really satisfy.
I don't think it would be that easy.
Yeah. All right, thank you.
Any more questions? I have a question, if you can give me an idea. I noticed that you had your retuned with transfer learning models performing slightly better than the ones that were supposedly optimized for each time series on their own. So any views why you got slightly better performance, even though you were using transfer learning up to a point?
So I'm not completely sure, but what I think is we focused our research on one type of the models of the winning methods of the M5, the recursive store level IGBM models. But we have also seen that the features and the hyperparameters that we took over from the winning method, that they actually slightly overfit on the public data set of the M5. So what I noticed when doing these experiments is that the models we base our research on are not, I think, not the optimal models in that sense. So maybe that could be a reason why we achieve slightly better results. So further research is necessary to also test it on different models that maybe do not overfit the public data set of the M5.
Thank you. There is time for one last question if anybody has, or otherwise you can use the chat while the next talk is going as well. May I ask if you let us to prepare your slides, and Arnold, if you stop sharing while people think for another question. 20 past, so we can proceed with your presentation.
Okay. Hey everyone, I'm Philotas Theodosiou. I'm a master's student at the University of Hovde, and this is our work with Nikos, forecasting with deep temporal hierarchies. So first of all, I want to give a brief introduction to temporal hierarchies. I want you to consider this series and this series and this series. So they all look pretty different, but in fact, they are the same series just observed from a different viewpoint. And that's the main idea behind temporal hierarchies. You can, through non-overlapping temporal aggregations, you can construct different series of different frequencies which carry different information. And if you stack them, you get this nice and beautiful hierarchy. So why to consider temporal hierarchies? First of all, they lie under the umbrella term of forecast combination techniques, and forecast combination techniques have been shown to offer accuracy benefits. They combine diverse information while they deal with parameter estimation issues, model misspecification issues, and this can be viewed in this example here. This is the previous trend seasonal series, and where most of its variance is due to the seasonality. So a model will have a hard time identifying the trend. So if we aggregate on the higher hierarchical levels, you can filter out the seasonality and you can see the trend here and even better here. So if you fit each model at each hierarchical level, you can extract every information available in the hierarchy. In addition, combining forecast reduces the aggregated variance in case the covariance of the combined methods is favorable. And lastly, forecasting with temporal hierarchies supports aligned decision between operational levels. So you can have an aligned strategy across all levels, leading to enhanced decision making. So how to forecast with temporal hierarchies? The general framework is FIF, the temporal hierarchical forecasting framework. What you do is you construct each hierarchy and you get a base forecast for each aggregation level. What you do next is you combine this base forecast using a reconciliation method, let me say, and then you sum up to the other aggregation levels, leading to the full reconciled hierarchy. The full formula can be seen here: base forecast, combine, multiplied with reconciliation matrix, and then sum up to the full reconciled hierarchy. The key question is how to actually reconcile. There are two lines of research. First, there are the analytical methods where researchers analytically try to estimate the matrix G. These are primarily linear methods based on multiple assumptions to soften some complex estimations, primarily estimations of the covariance, because if you have this big, deep hierarchy, if you try to estimate the covariance, it will be extremely difficult. So researchers rely on some assumptions, but under these assumptions, we lose some information regarding the relationships between the aggregation levels. So we partially consider these relationships and we lose important information. And the other line of research regarding machine learning, we have soft constraints in the, they can be viewed as terms on the loss function, extra terms, which try to teach the model to be both accurate and coherent. However, coherent is not ensured. And then we have local-based nonlinear methods trained on individual time series, don't train globally on multiple models, which might increase their performance. So what we aim in this work is to introduce deep learning to the field of temporal hierarchies. And temporal hierarchies are composed of two major components. We have base forecast and we have reconciliation. So what we want to do is we want to introduce a solution to both tasks individually. Regarding reconciliation, we want to take base forecasts and reconcile them using a neural network, achieve accuracy, and if we achieve coherence is also a bonus. And then what we also want to do is increase the accuracy of base forecasts using deep learning. And how we aim to do that is, instead of considering a single hierarchical level to produce a base forecast, we combine we take information from all levels of the hierarchy, we consider the correlations to produce a single forecast. And then you have this deep learning saying that says that, okay, if you have two models which are the results of the one are correlated to the results of the other, it's much, much better to train the model end to end. Start with one and end on the other. So on the last step, we jointly forecast with temporal hierarchies. We mimic FIF, and instead of training two individual models, we train a single framework. Why we do that? We want to merge the theoretical principles of FIF, the theoretical principles of forecasting with temporal hierarchies, with deep learning. We want to overcome aforementioned limitations, linearity, assumptions, and the partial covariance estimation, and use these principles to design a deep architecture. So how to do that? Okay, so what FIF does is takes base forecasts and combines them into the bottom level. This is what an encoder-decoder architecture does. It takes something, it compresses into something, a low dimension, and then it reconstructs something else. So we view this neural network approach as an encoder-decoder. It's called a reconciler. The model, we take base forecasts, we feed them into a neural network, we compress it to the bottom level, and then somehow we construct the entire hierarchy. So G is viewed, instead of being viewed as a reconciliation matrix, it is viewed as a trainable neural network. And here comes a key question: how to optimize that model, how to train that model. We follow three different optimization methods. First, we have this SUB method, which is the most basic approach, let me call it, which we combine base forecast into the bottom level here, and then we simply multiply with the summing matrix S to get the full reconciled hierarchy. It's the same approach followed by FIF. The model, the neural network here is trained on producing good bottom level forecast, and that's what only it is trained on. But what if we could optimize the level, not on a single level, but produce good predictions across the full hierarchy? So that would give the model extra information, that would regularize the pre-training of the model. Coherence will work as a hard constraint, as a regularization factor. So we take this matrix S, the summing matrix S, and we internally add it into the architecture in the form of frozen layer with frozen weights, no trainable weights. So we train to optimize the bottom level, then we have these fixed weights equal to the summing matrix. And in one sense, we train to optimize the full hierarchy. And finally, we have another architecture, the simple encoder-decoder, train an encoder, and then train a decoder separately, a trainable decoder, which doesn't ensure coherence. Then we move to base forecast. We use exponential smoothing as benchmark because it is widely applied on such tasks, easy to optimize, good overall performance. However, it is fitted on a single hierarchical level. What we want to do is consider information from the whole hierarchy. And how to do that? You don't have anything better than a convolution layer, a 2D convolution layer to model local relationships between small neighborhood pieces. And this is where our architecture is based. So this CNN LSTM architecture, the hierarchy is in the same format as images in a computer vision task. We have this grid here, and to convolution scan this image to identify relationships. And then we feed it into an LSTM to model the long-term relationships. And finally, we forecast. This is an architecture which is used on every hierarchical level. So every hierarchical level is trained on this architecture. And this is a limitation. This is a limitation because we are training 7 neural networks, 6 for base forecasting, and 1 reconciler if we are trying to predict monthly hierarchical series. What we want to do is we want to train a single model. We want to take all benefits, the modeling of these model local relationships, the modeling of the long-term dependencies using LSTM, the optimization across the full hierarchy, the regularization of the training, and maybe the mapping of the bottom level to the full hierarchy, combine them into a single joint framework, train end-to-end. And this is what deep temporal hierarchies is. It takes every information, every benefit of the proposed models. We have the shared architecture, scanning the full hierarchy, modeling dependencies, and then we use a multitask approach. So we have a shared layer, task-specific layer for each hierarchical level. We're training a model, a layer for annual levels, a model for a monthly level. Training this layer regularizes training of this, regularizes training of this. So each layer helps training the other, and all of them help training this block here. We have 2 different use cases. One, we output the predictions, which are not coherent because I have not added something to ensure coherence. But what we can do if we cannot tolerate with a small reconciliation loss, we can just keep the bottom level and sum up by multiplying the summing matrix. Moving to the experimental design, we have data from the M4 competition, 2 samples of monthly time series. To fit the reconcilers, we use 2 approaches, a per series approach, fitting a reconciler to each time series with a sliding window to construct training instances. And then we train globally on 15,000 time series using 50-fold cross-validation. And since we talk about forecast combinations, we should use ensembles, of course. To evaluate 50, we use ensembles of 50 reconcilers. To evaluate, we use mean absolute scale error on 2 comparisons, one on the bottom level and one on the full hierarchy. stacking predictions in the vector, and calculating their mean absolute scale error. So moving the comparison experiments, we have two experiments. First, comparing the individual components, the reconcilers, and the model for base forecasting. And then we're comparing the joint performance. So these are the benchmarks. For the reconcilers, we are taking base forecast from exponential smoothing, and we are comparing all the defined reconcilers with the non-reconciled predictions and with reconciled predictions with structural scaling. Every method is stiff, everything is stiff. When we get base forecast and reconcile with everything is stiff. But for notation issues, we refer to the statistical usage of stiff here. And for the joint performance of deep temporal hierarchies, we have multiple models. We have this defined architecture, the individual predictions, the reconciled predictions. We reconcile each base forecast with multiple methods, and then we reconcile the predictions of exponential smoothing. Moving to the results, I should mention first that mean here is influenced by outlier predictions, and median gives a better indication, a more representative indication of the performance of the model. However, what mean shows is how models handle outliers, which models produce outlier predictions, and this is why it is included. So what we can see on the local fitting of the models, the submodel fails, but COH28 with a frozen layer and the encoder with a trainable decoder produces competitive performance with TIFF. And when we train globally on multiple time series where neural networks excel, we see that all models outperform conventional approaches. And in general, the reconciler with the fixed weights produces the best results. And here comes the question, why is that? Is that because of coherence as a regularization? Is it because we optimize on the full hierarchy? Is it because of both? We will answer that later. Moving to the base forecast, we see that these are the results of the base forecast experiment. So the proposed architecture outperforms exponential smoothing on its hierarchical level. And this is especially the case for upper aggregation levels, for bi-monthly, quarterly, 4-month, and semi-annual levels, where we don't have enough training observation. For example, if we have 12-monthly observation, we have only 3 quarterly or 4. And this is what this architecture excels at. You don't have to have a lot of training instances. We can, for an annual prediction, we can consider information from the lower levels and from the local relationships and produce good enough annual predictions. You can see here, compared to exponential smoothing, which is only one time series, only the semi-annual level, we can see much better performance. Why? Because we consider all hierarchical levels. Okay, so deep learning models, when trained globally, produce good results. Here we see the joint predictions, the performance of deep temporal hierarchies, which considers all the benefits of the models. It is observed that the joint framework produces the best performance. It outperforms all other models. However, we see that CNL with the coherent reconciler produces here good results. However, and we said you have to train 7 models. You need a lot of time. You need a lot of data. And with the joint framework, we just train 1 single model. What we also see is the effect of base forecast on the overall performance. We see that when we reconcile predictions from exponential smoothing, the results are worse than on the bottom level. I mean, they are worse than base forecast from exponential smoothing. But the intuition says that what we want is we want good, accurate base forecast across the full hierarchy, not just the bottom level. Exponential smoothing didn't produce good results on the higher hierarchical levels, and that's why maybe the reconcilers fail. Because if you see the performance of the reconcilers on the more accurate performance of the base forecast method, it produces better results than the base forecasting model. This is another interesting finding. Finally, we see that the coherent model with the frozen weights outperform the other reconciliation methods. And to conclude the findings, we see that, okay, we can use deep learning models to design individual components, we produce competitive performance, but if we combine them into a single network, we get the most accurate predictions. So moving to the previous question, why is this coherent model with a frozen weight better? Firstly, let's see how each model considers coherence. So we have the S-sub models. The S-sub model, we just use coherence as a stepwise function. You map bottom level predictions into the full hierarchy. Then we have coherence as a regularizer. So COC28 uses coherence as a hard constraint, as a regularizer, forcing predictions to be coherent. So the fixed weights force the predictions to be coherent. Finally, encoder-decoder doesn't consider coherence at all. The results suggest that coherence as a hard constraint is beneficial. It gives the best overall performance across all experiments. So what coherence does as a regularizer is it drags all predictions into the coherent subspace here, and every iteration the neural network makes, it's a step closer. But this coherent subspace, it's much smaller compared to the accurate subspace. So the weight combination and the total weights are less. So it helps the optimization of the model. It helps converging. And this is maybe why this model produces the best results. So using coherence constraints can help in optimized training, can uncover new subspaces, these subspaces here, which conventional approaches might not have seen. And finally, I want to talk about, I want to touch a discussed limitation of deep learning. So we know the major limitations of deep learning models, their explainability, transparency. These are very important topics. Hopefully researchers will find solutions to this topic. And here we come to the data hunger problem. So it is believed that deep architectures require thousands of data. And this is most of the times true. Deep architectures require a lot of data to be trained on and to produce competitive performance. However, we can see here DTH with just 500 series outperforms exponential smoothing. And as we increase the training observation, its performance gets better. So sometimes, okay, this is on the specific task. I'm not saying that it is a regular topic, but sometimes no, it's not about adding more and more data into a deep architecture. It's not about taking a single neural network, a single fully connected network, and adding more and more data and trying to get better results, because this won't be the case. Sometimes it's about designing smarter architectures and helping the model achieve better performance by considering theoretical principles. So my conclusion is that it's not always about the data, it's about data and smarter architectures. And this is how I want to conclude. We talked about how deep learning can be introduced to the field of temporal hierarchies, how it can be trained globally, and how it can be used as an alternative to well-established methods. We're not suggesting that it should replace everything, but it should be another tool in the toolbox as a reconciler for base forecasting or even train end-to-end. Another interesting finding is that coherence as a regularizer is beneficial. And I am in some future work, we aim at investigating in a bit more how we can take advantage of coherence and achieve better forecasting accuracy. And yeah, that was my presentation. Thank you for your attention, and I'm happy to answer any questions.
Thank you, Filota. There is time for some questions. So please either use your microphone or the chat.
Hi, that's Weber speaking. So I would like to ask you first is why 15K, not 48K of time series?
Sorry, I didn't get
You
that.
use 15,000 monthly time series from M4 and the whole set is 48. Why 15?
Because I didn't want to use the full set. If I had more time, I would use a smaller subset because most of the times it's not available to have this vast amount of training time series, and the M4 competition gives a lot of time series, but this is not the case in most scenarios. So I would like to have as fewer time series available as possible, and that's why I have included this graph here.
Okay. And how long did it take you to run one single run?
That's a very good question, which, to be honest, I don't remember, but I was using a GPU, so it wasn't more than 2 to 3 minutes. And the full ensembles, like I was using for the reconcilers, I'm using 15 ensembles, so the total training time was at max 5 to 10 minutes for all 15 ensembles.
That's pretty quick. Okay, that's very quick. And also in some of the slides you are showing errors, average maze, I assume, of
Yes.
exponential smoothing, and so I have trouble believing that it's maybe not here, maybe it's somewhere where there I see that,
Here?
yeah, like ETS, like average performance of your month, average May is 3.7, and then ETS. I mean, it's difficult to believe you are beating ETS 20 times. I mean, what happened? I mean, median is reasonable, but so what happens? Why you have monster errors on some of these?
These are on the full hierarchy. So if we here is when some extreme outlier predictions on the full hierarchical level contribute to these.
I was running also
average.
I've never seen something like that. I was running ETS on all-time series, and I've never seen monster errors on exponential smoothing. Your median maybe is reasonable, but this is really strange to me.
One possible, I can give you a possible, I have not thought about it, but a possible answer is that I'm using a Python version of exponential smoothing. So maybe it's the fitting strategy, which...
All right, if you use Python, everything is clear. Okay.
Yes, this is because
okay.
It's a different package.
All right, okay, thank you. Thank you.
The 20 minutes have formally finished, but since there is no other talk, there can be Q&A for both talks if people want to stay. I will keep the session open, so feel free. Otherwise, please proceed to the next session. And don't forget to rate the presentations.
Okay, so one more question. You're doing coherence in your through encoder decoder. Did you consider doing that stuff through loss function?
In the form of soft constraint. Yes, but this is a very good question. In fact, I argued against soft constraints in the beginning in the form of extra terms on the loss function, because I thought coherence was also important to achieve, because if we add these coherence, these soft constraints on the loss function, the model would not learn to produce coherent predictions. But then with the help of Nikos, of course, I figured out that coherence is not so important at the end of the day. We just have to produce good bottom level predictions and then multiply with the summit matrix. So yes, it's a very good alternative to add them on the loss functions to also regularize training this way.
Okay, thank you.
I see people are dropping out, so if there are no more questions, Philotas, we'll let you relax. Arnaud, I don't know if there are any questions for Arnaud as well. He's still here. Or otherwise, I can just say to everybody, enjoy the rest of the conference.